Hi, I'm Natalie. I'm a developer on the Direct3D team, and I'm here today to talk about the different presentation models on Windows 10 and their various performance characteristics, and to give some tips on how to use them properly for your games. So the first thing I'm going to do is I'm going to give an overview of the different types of presentation models and some relatively simple properties that they have. So the first presentation model is the windowed blit presentation model. This is the D39 swap effects of copy or sequential, or the TXGI swap effects of sequential or discard. Basically the way it works is you have your application back buffers on the left, you have multiple of them, you render into those, and then when you call the present API, on your behalf the operating system will copy the contents from your back buffer into an intermediate surface, and then eventually the desktop compositor will take the contents from the intermediate surface and will put it into your window on the final desktop image. This is the most simple type of presentation model that we have, and it has some additional overhead compared to some of the others. So there's an additional back buffer sized surface in order to contain the copied contents, and there are 2 copies involved in the process. There's one copy from the back buffer to the intermediate, and then a second copy during the composition process. Everyone knows that if you take your windowed swap chain and you set it full screen, you get some additional performance. So next I'm going to talk about full screen. There's a couple different ways that a full screen swap chain can run. The most performant and the simplest one is the flipping mode, where you have one buffer that is always on screen, and then you have a second buffer that you're rendering to, and then you just flip them. And the buffer that you were rendering to becomes the one on screen, and the one that was on screen is the one that you start rendering to. And you can obviously do triple buffering if you need to have 2 buffers ready to go, but that's the general idea, is that you flip between your back buffers directly to the screen. Taking it a step further in complexity, we can do a blit type of full screen presentation where you have one buffer that's always on screen, and then the present operation is simply copying your newly rendered contents into that buffer on screen. Or if for some reason you're not able to do a regular type of flipping presentation mode, the operating system actually has a blit plus flip type of presentation that we call proxy. And in that scenario, you have your back buffers that you're rendering into, and the operating system has 2 full screen front buffers that we will copy our contents into and then flip it to the screen. And as you can see, the full screen flipping type of swap chain has 0 overhead, no additional copies, and no additional surfaces. The blitting type of swap effect has 1 additional surface and 1 copy, and the full screen proxy actually has 2 additional surfaces and 1 copy in the presentation process. So these are to be used sparingly. The ideal for full screen applications is to use the flipping type of presentation. The way that you do that is a D39 sequential or discard swap chain, or a TXGI sequential swap chain with more than 1 buffer, or a TXGI discard swap chain as well. In order to use the blit type of swap effect, you would use a D39 copy swap chain in full screen, or you'd use a TXGI sequential swap chain with 1 buffer. And the proxy is something that you really never want to try to use. It is done on your behalf if for some reason your buffers are not capable of actually being put on screen directly. Moving on, something that we introduced in Windows 7 and made available to TXGI in Windows 8 is the windowed flip model type of presentation, which has some advantages over windowed blit model and has become increasingly useful as a replacement for the true exclusive full screen type of presentation. So the way it works is you have your back buffers that are shared directly with the desktop compositor. So there's no additional copy in order to make the contents available for the compositor. There's just the 1 step of composition directly from your back buffers to the final desktop image. As an enhancement in Windows 8, we enabled a new feature which is called Direct Flip. The way Direct Flip works is that the compositor will detect that your window covers the entire screen and will actually decide not to compose. it basically takes itself out of the picture and puts the app's contents directly on screen, which removes the additional copy, or the composition step. Further, in Windows 8.1, we introduced a new feature, which is independent flip. In this scenario, DWM further removes itself from the picture and actually gives agency to the application process to continue to put its contents directly on screen. And there's a new feature, which I don't have a particular image of because it works the same as independent flip, which is what we're calling independent flip with true immediate presentation. And the way this works is basically the application not only has the ability to put its contents directly on screen, it has the ability to do that at any time in the middle of a vsync. Basically, this enables flip model applications, windowed applications, to have tearing where they previously wouldn't. So, talking about the properties of that, windowed flip model swap chains have no additional surfaces, regardless of how they actually end up on screen. And most of the time, you can actually get away without the composition step if you cover the entire screen area. Moving forward, the next concept that I want to talk about is the frame latency of these different types of swap chains. So first, the definition, what I'm talking about. Frame latency, as I'm defining it, is the time from when, for example, a scene traversal happens, when you decide what you're going to draw, to the time that it actually appears on screen. So the simple case of a windowed flip model swap chain or a windowed flip model swap chain, with vsync off, this is you're presenting with sync interval 0. This is basically you want to present as fast as possible. You want the contents on screen as soon as possible. In this scenario, the total amount of latency, the minimum amount of latency that you can achieve is a little bit over 1 frame. And the reason for that is basically the app is presenting over and over and over again. I'm going to trace this red frame as it makes its way to screen. Finally, right before the vsync happens, the app presents its last frame, and immediately after the vsync, DWM wakes up and starts consuming those contents. It produces a desktop frame, and it queues the presentation of that frame to happen on the next vsync. So from app rendered to DWM rendered, finally to screen, is 1 frame of latency. Basically, it's the amount of time it takes to do the composition and put it on screen without tearing. Once you start talking about full screen with vsync off, you can present as fast as you want, and it makes it to screen immediately. There is 0 latency. This is also true of the independent flip with true immediate flips, the new presentation that I was talking about. As soon as the app renders and presents its contents, it is on screen immediately. No latency at all. However, once we start talking about apps with vsync on, the latency starts to get a little bit harder to picture and a little bit harder to manage. So as most apps know, basically the way a render loop would look is you do your render and then you do present, and at some point the system is going to throttle you in order to make you run approximately at the vsync rate. So the way this actually works is that we will block in the present operation, but before it gets submitted. So what we see is that an app will start the frame with a present already pending from the previous frame. And then I'm going to trace this red frame again. The app will start to do the scene traversal, will render its contents, and it will have a frame ready to go on the GPU sometime during this vsync, assuming that it's running at 60 FPS. But then that present doesn't actually make it to screen. Sorry, the present doesn't actually make it to DWM until the next vsync has already happened. And at that point, DWM won't start to pick up those contents until another vsync has happened. So what this actually means is that you get almost 3 frames of latency when you use vsync in a windowed swap chain. In a full screen swap chain, if you have vsync on, you have basically the same problem. You have 2 frames of latency because there's no composition frame. DWM doesn't take a frame out of that to do the composition. However, you still are blocked to present before it actually gets submitted, and then you have almost an entire frame of just sitting there waiting before it'll actually get queued to be presented. And then once it's finally been queued, it'll make it to screen on the next vsync. And then I mentioned before that there is a full screen blip type of presentation. The main advantage that this has over any other type of presentation is that it does actually get you 1 less frame of latency. because you don't block in present until after the vsync happens. You block in present until just before the vsync happens, at which point you can finally actually submit the blit operation and have it get on screen basically immediately. However, I would not recommend this because there's no guarantee that this will not cause tearing, even if you do vsync, if the operation takes a little bit longer. A new feature that we introduced in Windows 8.1 is the TXGI waitable object swap chain. And the advantage here is that it allows an application to reduce its minimum frame latency by approximately 1 frame by using it in a particular way. The recommended usage pattern is at the beginning of your frame, after you've presented the previous frame, but before you actually start doing your seam traversal and render ops, you want to issue a wait on the back buffer sync object. So what that looks like is that you'll notice there's no previous frame that's coming into this picture here. The app actually starts rendering the keyframe immediately, and as soon as the rendering is completed, the present is submitted, and DWM will pick it up on the next frame without having to wait for the extra frame of lag. And then once DWM completes the composition, it will make its way to screen in almost 2 frames of latency, which is significantly better than the 3 frames that you get from a standard window presentation model. Moving forward, we have the Iflip presentation model. The standard Iflip presentation model looks basically just like TXGI full screen or D39 full screen, where you have 2 frames of latency because you're sleeping in present like normal. However, if you use the waitable object combined with an independent flip swap chain, what you can get is just about 1 frame of latency. The app wakes up on vsync after the waitable object is signaled, can render the frame, submit the present, and it'll be queued to make its way to screen within that same vsync. So right on the very next vsync, it'll actually make it to screen. So a quick recap of the properties I just talked about. We've got windowed blit with vsync off and windowed flip with vsync off. You get just a little bit over 1 frame of latency as you're submitting your presents continuously, and the last one will make its way to screen. In the full screen type of presentation, you have 0 latency because as soon as your rendering is complete, the contents make its way to screen, which introduces tearing, hence the vsync off tearing factor that most people are used to. For example, if you have a settings menu and you show vsync off, that's what most people expect to see. They expect to see tearing. And then the independent flip type of presentation cuts out one of that extra frame of latency from the windowed flip presentation path. And like I mentioned before, the new true immediate iflip type of presentation has 0 latency, just like exclusive full screen. Once you start talking about vsync on, you start talking about almost a certain number of frames. The notation here, the plus means just a little bit over 1 frame, 3 minus means almost 3 frames. So once you start talking about vsync on, you start talking about pretty high amounts of latency. The best way to reduce this latency is to use full screen swap chains or to use the waitable object swap chain. Moving forward, start talking about another concept, which is the concept of frame queuing. So the definition that I'm using for frame queuing is how many GPU completed frames are waiting to be flipped to the screen. And a number that I have in my chart is this n, where n is the minimum of the swap chain buffer count and the maximum frame latency. So for TXGI, for example, you can create a swap chain with 2 buffers, and what that typically means is that you can only have 2 frames queued before you need to actually wait for the GPU to render another frame. You can also control that if you have, for example, a 5 buffer swap chain, but you set your maximum frame latency to 2. That still means that you can only have 2 frames that are completed on the GPU before you need to wait for another one to complete. So it's the minimum of these values. Having a high frame latency doesn't help you if you don't have more buffers to render to, and having a high buffer count doesn't help you if you don't have a higher frame latency to compensate. So I'm just going to go ahead and go over the chart. I don't have any fancy pictures for this. So a typical windowed swap chain using the blit swap effect only has one frame that can be queued before the GPU needs to wait to render another frame. The reason for that is because there's only one intermediate surface that's shared with DWM. And that's where the contention happens. Before you can actually start rendering another frame, you need to wait for that intermediate to become available again. The full-screen blip type of presentation has basically the same problem. There's one full-screen surface that is on screen. You need to wait for that to become available before you can blip to it. Note that frame queuing actually only makes a difference when we're talking about vsync on. When vsync is off, the GPU basically runs as fast as it possibly can, and there's no need to queue multiple frames. Once we start talking about the proxy type of full screen, there's two front buffers. So again, the maximum frame latency that you can have in that type of presentation is 2. The full screen flipping type of presentation, as well as all of the windowed flip model presentations, allow what we call deep frame queuing. You can get all the way up to that magical n number, which is your buffer count or the maximum frame latency. And what's the advantage to using a higher frame latency versus trying to shoot for low latency? The main trade-off is that obviously low latency is good for input critical situations. You've got that Twitch shooter, you need the mouse input immediately on screen. Whereas something with a high max frame latency allows you to hide any kind of hiccups and keep a smooth frame rate while doing so. So if you've got 3 frames ready to go, and one frame takes twice as long as another for whatever reason, you've already got those ready to be consumed by the screen. Go ahead and talk about frame rate. So this is a property that everybody is highly concerned with. So obviously when you have vsync on, your frame rate is going to be tied to the refresh rate of your monitor, typically 60 Hertz. However, when you have vsync off, your frame rate can be significantly higher. And your frame rate is typically limited by what type of presentation model you choose. So the windowed blip presentation model, along with all of the full screen presentation models, will allow unlimited presentation rate with a vsync off swap chain. However, the current biggest drawback to the windowed flip swap chain type is that it does lock your frame rate to a multiple of the vsync, depending on how many buffers you have available. The best way to explain why this happens is that basically DWM is holding on to one of your back buffers in order to be able to compose. So if, for whatever reason, your app decided not to present another frame, DWM still needs to be able to recompose the desktop from scratch. So it needs to always have a buffer from the app that has recent contents that it can use to compose a new desktop frame. So when an app presents a new frame, what that tells DWM is that it can start consuming that new frame instead. However, DWM doesn't really notice this until it wakes up on the next vsync. So if you present with sync interval 0 and you present 5 times in a frame, what you'll actually find is that DWM will pick up the last present, but it won't actually release the old buffers, those first 4 presents to you, until it wakes up on the next vsync. So for a simple example, if I have a 3 buffer swap chain and I'm in steady state, what that means is that I can present 2 buffers in a single vsync, and then on the next vsync, DWM will wake up and release the buffer that it was holding on to and one of the buffers I presented, and it will hold on to the 3rd buffer I presented. So that's where all 3 buffers go. And what that means is that you can present twice per vsync, giving you a maximum frame rate of 2 times the refresh rate. So basically the little formula is the refresh rate of the monitor, typically 60, times the number of buffers in your swap chain, minus 1. Unfortunately, the direct flip type of presentation, which does optimize out a composition step, also adds a frame where the system is holding on to one of your buffers. So what this means is that a 3-buffer swap chain will unfortunately only run at 60 Hertz, or at the refresh rate of the screen, when you are in the direct flip type of presentation. Fortunately, direct flip on Windows 10 is used very sparingly. It's almost exclusively used as a stepping stone to enter the independent flip type of presentation. And in independent flip, you have, again, the same limiting factor that you do when D to Wim is doing the composition of the desktop, because one buffer is held onto by the screen. And you can present several times, and on the next vsync, one buffer is returned to you from the screen. You can start writing to it again, and the other buffers that did not get put on screen are again returned to you as well. In the true immediate iflip type of presentation, the buffers are returned to you as soon as you flip a new one to screen. So what this means is that an application using the true immediate iflip presentation mode can still present at an unlimited, unthrottled frame rate. Another interesting detail that isn't always important, but sometimes comes up, is when the back buffer needs to be synchronized. So specifically this is, let's say, I have a simple application and I just render straight to the back buffer at the beginning of my frame. What does that actually mean for me when I'm using a full screen presentation or when I'm using a flip model presentation? So the question that we're trying to answer here is, when does the GPU need to wait for a new resource to become available before it can continue making progress on the frame? And under normal circumstances, that actually happens as soon as you make your first write to the back buffer. So in a true full screen swap chain where I'm flipping one buffer to screen and then the next buffer to screen, I can't actually start writing to a buffer until it comes off screen. So what that means is the GPU is going to be blocked until the next vsync happens, and I can start writing to screen again. I can start writing to the back buffer again once it comes off screen. And the same type of behavior is found in the windowed flip model presentation, because like I said, D to Wim is holding onto the buffer, not the screen. Well, sometimes the screen in independent flip. But basically, someone is holding onto your buffer, and you can't start writing to it until that component gives it back to you. So that is the first render type of entry in this column. The other type of presentation, or the other type of synchronization happens, for example, in the windowed blit type of presentation. I can start rendering to my back buffer immediately. It's not until I actually call the present API that my GPU is going to get throttled, waiting for that intermediate surface to become available again. In that case, the intermediate is actually the surface that's being shared between components, and that is where the synchronization happens in the frame. So this isn't usually relevant, but sometimes can indicate why your frame rate might not be as high as the theoretical maximum that I listed before. So if, for example, the theoretical maximum I have is vsync times 2, but I'm only getting 90 FPS, one of the reasons for that might be that the GPU is getting blocked a little bit earlier than you might expect, because you start writing to the back buffer maybe halfway through the frame. So one way to work around this kind of behavior is to use another intermediate, an off-screen render target, and avoid writing to the back buffer until the very end of the frame, some type of color resolve or a multi-sample resolve as well. And then moving on to some simple properties, some simple yes-no properties. Can my swap chain tear if I'm running with vsync off? The simple answer is, are you in a window? The answer is no. If you're full screen, the answer is yes. The only exception is this windowed iflip immediate where you are covering the entire screen, and for all intents and purposes, you are actually full screen. In that case, yes, you can tear as well. The question is this API exposed to D312? The answer is, for all true full screen swap effects, as well as the windowed blit swap effect, the answer is no. The only swap effects that are available to D312 are the windowed flip swap effects. However, this does include the true immediate iflip presentation mode. And then the question is, how do I actually use this API? How do I use this type of presentation? What APIs do I use? So for the windowed blit presentation, if you're running in a window, there's a couple swap effects you can choose. Like I mentioned earlier, D39, you've got discard, copy, or I think flip is the name. In DXGI, you've got discard or sequential. If you want to run in full screen, you create your full screen swap chain, and depending on which swap effect you use, you'll choose between flipping and blitting. The only case where you end up in a proxy type of presentation is where you choose something that is not quite compatible with the screen. For example, maybe your refresh rate was wrong, or you requested a particular scan line ordering, but the screen didn't actually support it. So in general, we recommend to leave those fields blank because they can put you in an inefficient type of presentation that we would like to avoid if possible. So that's why it's not quite API exposed. You can trigger it if you get something wrong, but in general, it's not something that you want to try to aim for. The windowed flip model swap effect is available to both D39 and D3011 and D3012. You choose the flip-sequential swap effect, or new for Windows 10, we have the flip discard swap effect, which I'll get to in a minute. And for D39, it is the flip-EX swap effect. dflip is not API exposed, nor is Iflip. In order to trigger either of those, you have to resize your window so that your contents cover the entire screen. And just hope that the OS actually makes the decision for you. Make sure that you resize your swap chain buffers once your window covers the entire screen in order to make sure that your swap chain buffers actually match the screen resolution. Another key point here actually is that on systems with overlay support, which most desktop systems don't have these days, but I believe that is a feature that is up and coming on the desktop. If your system has overlay support, you can query this from TXGI output to check overlay support. When overlays are available, any windowed swap chain can be promoted into direct flip and independent flip. You do not need to cover the entire screen. DWM or the application is capable of flipping to the screen in a different plane than the desktop. So you can actually have contents that are on top of the desktop without needing to cover the entire screen. The true immediate iFlip presentation mode that I've been mentioning so far is not actually API exposed to D39 or D3011. It is currently exclusively reserved for D312 as a replacement for the true full screen APIs. So the way to trigger it is if you call the full screen APIs for a D312 swap chain, it's actually not going to create an exclusive full screen swap chain, it's going to create an independent flip swap chain. So now you might be asking yourself, why would I choose to try to use a flip model swap chain over a true full screen or a flip model swap chain? And the best reason that I can give you is that it provides a better user experience. One is that it doesn't cause the screen flashes that you might see as your app tries to go full screen or as you try to change the resolution. Another answer is that it allows the system to continue to compose on top of your application if necessary. For example, let's say the user chooses to change the volume while they're playing your game. In a true full screen application, the user has no idea what their new volume setting is. They just have to listen and hope that they got it right. But for an app that chooses a window flip type of presentation, most of the time they're running in a very efficient type of presentation. But when the user actually tries to bring up the volume display, they get to see it because the system drops back to composition. Now I mentioned earlier, a new swap effect that we have added for Windows 10 is the flip discard swap effect. The main advantage of the flip discard swap effect is that it enables an optimization in just the scenario I described before. If the user brings up some type of system UI on top of your game that covers a small portion of the screen, the compositor may actually choose to continue to use direct flip. However, instead of taking your contents and putting it directly on screen, and instead of copying all of your game contents, which might be a pretty big surface, into another pretty big surface in order to put it on screen, the compositor can actually choose to take the system UI and put it directly on top of your game contents before putting it on screen. This can save a bunch of time and space in order to reduce the number of surfaces that are required to get contents on screen. I'm back after a short break, and I'm here to talk to you about a little bit more. Time to dive into the D312 specifics of the talk. So we've had some questions from our early access partners who are trying to figure out how to correctly use the information that I just provided to get the best experience for their D312 apps. So the first question that we've gotten is, what is the right thing to do to replace my D311 game, use a discard swap chain? How do I make that work in D312? So there's two parts to that. Obviously there's the technical part of, well, you have to go and you have to have a multi-buffered swap chain, and you need to do manual buffer rotation, you need to actually write all the individual buffers in your swap chain. That's the hard part. But then the question is, how do I tune it? What do I need to do to actually get the right perf? So one trick that we have that we can recommend is for benchmark scenarios where latency isn't as much of a problem. If your discard swap chain was just to get high frame rate numbers, but not necessarily to provide the most recent contents, then what you can do is you can use the waitable object swap chain in a different way than you might expect. Instead of using it to wait for a new buffer to become available to render into, what you can actually do is you can use it to test whether a new buffer is available. So what that means is that you would go ahead and you would render your frame, and then right before you call present, you would call into the waitable object swap chain to wait with a timeout of 0. You can check the return code to see whether or not that was a successful wait. If it was successful, then you can call the present API and submit your frame to the system, and it'll eventually make its way to screen. But if the wait was unsuccessful, then what that means is you should just keep rendering. You should render another frame into the buffer that you have. And what that'll do is that'll let you get a high frame rate number while actually testing both the CPU rendering code and the GPU rendering efficiency. But not every frame actually has to flow through the presentation system. So you can produce a high frame rate number while actually only presenting one frame every vsync. So that is something that we can recommend for a benchmark mode for an app such as 3DMark or anybody who wants to do any kind of GPU performance profiling. However, any type of game, that's not something we would really recommend because that produces significantly higher latency than just using a multi-buffered swap chain and letting yourself get throttled to the vsync rate. Now, something to be aware of is that if you are running in a window, then it doesn't matter how fast your game is actually presenting. A discard swap chain is going to have the same number of frames actually make it to screen as a flip model swap chain. And that's because DWM only composes at the screen refresh rate. So even though you may have a high number showing on screen, that doesn't actually mean that a user is going to see that many more frames. Of course, it's a hard thing to explain to users, so one other question that we've had from our early access partners is, what does it mean to show settings on a menu such as vsync or triple buffer in the face of a D312 flip model swap chain? So the one thing that's kind of interesting is that for a 2-buffer swap chain with flip model, vsync on or off doesn't really make that much of a difference. You're still going to be able to present one frame per vsync because unfortunately you're throttled to the DWM composition rate. For a 3-buffer swap chain, choosing between vsync on or off is a question of 2 different things. It's a question of whether you want faster frame rates or smoother frame rates, and a question of whether you want lower latency it's a question of whether you want higher frame rates and lower latency versus smoother frame rates. Whether you care about seeing your frame rate occasionally dip from 60 to 30 or 60 to 45, or whether you want to be able to present at 120 and get the smoothest contents on screen. So, nice little chart to help you remember for the people that are looking at the final slides. Vsync on, off. We have 3 buffers and 2 buffers. Vsync on with 3 buffers gives you smooth 60 FPS. Vsync off with 3 buffers gives you low latency and 20 plus FPS. With 2 buffers, unfortunately, you still get 60 FPS and 60 FPS. So the question of whether or not to show a triple buffering option on your menu, my vote would actually be don't even bother. I would recommend that most game engines use a triple buffered swap chain, regardless of the settings that the user may choose. And I think that about wraps up our talk for today. I'm Natalie on the D3D team. Thank you for watching. Please get in touch with us. Let us know any other topics that you want to see. Let us know what you think of this video, if there's anything else that needs to be covered. And I'll see you later.